Okay, welcome to the third angular video. We're looking at kinetic energy and moment of inertia. This is where the rotation is going to start to become more interesting. So far, really all we've done is said, well, we can treat rotation a lot like linear motion. We can define angular position, velocity, acceleration, use the kinematics, relate it to the linear variables. Really, the only particularly interesting thing we've done is the difference between tangential and radial acceleration. But now we're getting into something interesting, and that is how energy relates to the angular variables. And one thing we're going to find is that almost every linear quantity we know has an angular equivalent. And so the one we're going to look at now is we want to look at we want to find the equivalent of mass. We already know that the equivalent of position is angular position. The equivalent of velocity is omega, the equivalent of acceleration is alpha, and we want to see if there's any linear equivalent of mass. To do that, we're going to look at kinetic energy, because for energy we know that 1/2 mv squared should be the same as 1/2 times something times omega squared, and we want to find out what that something is. So now let's imagine some rigidly connected point masses. So that means we've got m1, we've got m2, m3, m4, and so on. There can be more of them, m5. And let's say that they are all connected so that they cannot move relative to another, and they're rotating about a pivot point there. So that's they all have massless connections there that make it so that they can rotate as a group, but they can't move independently. And so this would be R1, R2, R3, R4, and R5. Now let's say the whole collection is rotating at angular speed omega. That means that m1 will be moving with speed v1, m2 will be moving with speed v2, and so on. And one thing that we notice is that the particles that are farther from the pivot point move faster, because we know that the speeds are given by omega r. So the larger r is, the larger the speed will be. And then we can calculate the kinetic energy of this system of particles. We know that kinetic energy is 1/2 mv squared. We just need to add that up for all the particles. So it's 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and so on, which we can write as 1/2 m1 omega squared r1 squared plus 1/2 m2 omega squared r2 squared, and so on, because remember, the speed of the particle equals the angular speed of the whole thing times the distance of that particle from the pivot. And so that gives us, we can bring out the factor of 1/2 and omega squared, because that's present in every term of the sum, times m1 r1 squared plus m2 r2 squared, dot, dot, dot. And we can use summation terminology to say that's 1/2 omega squared times the sum of mi ri squared, where we sum over I. And if you look at this, if we call that sum the moment of inertia, I, then we find that the kinetic energy equals 1/2 I omega squared, which is a formula of exactly the form that we wanted to have over here. So m is going to be equivalent to this moment of inertia, and that's what's going to go in here. And so our equation for kinetic energy has a rotational analog, just like everything else, as long as the moment of inertia is defined to be that, the sum of the masses times their distance from the pivot point. Now notice that the moment of inertia depends on the axis. In general, you're going to have the smallest moment of inertia when kind of the average distance from the axis is smallest. And so that means something rotating about its center of mass is going to have a smaller moment of inertia than something that is rotating about its edge. And before we go on and learn more about how to calculate moment of inertia, let's talk about the difference between kinetic and translational kinetic. Pardon me, that should not read kinetic, it should read rotational. Rotational and translational kinetic energy. If we imagine something that is moving, the term for this is rigid body, meaning it can rotate, but the different parts of it cannot move independently of each other. So let's imagine a wheel. That's kind of your typical example. And it's rolling, so it's rotating about its center of mass with speed omega, and it's also moving with speed v, the center of masses. So the translational kinetic energy is 1/2 mv squared, where v is the speed of the center of mass. And then rotational kinetic energy is 1/2 I omega squared, where omega is the angular speed about the center of mass. And then v is the speed of the center of mass. That's very, very important, that v is the speed of the center of mass. It's not the speed of any other point on this object. Now, to calculate the moment of inertia, we know how to do it for collections of discrete objects. We find the mass and the radius of all of them, sum up all the masses and the radii, mi ri squared summed over I. If you're not comfortable with the summation notation, that's what it comes out to be. And it's not difficult. It can be tedious if I exceeds, say, 3, but it's not difficult to do. However, we're really going to be more interested in finding the moment of inertia for solid objects, like, for instance, a wheel or a disk, where you can't break it up into 4 or 5 point masses. However, what you can do is break it up into lots of little tiny mass elements, dm, all of which have a particular radius, and then you can sum up all of the dm's. So that'll be the sum of r squared times dm. And if we make dm very, very, very small, we'll get an integral. This is a Riemann sum, r squared dm. Now, for those of you in Calc BC, you should, at some point this year, learn how to do calculations of this sort, two-dimensional integrals. I'm not going to show you how to do this in this class yet. We might do it near the end of the year once you have more calculus under your belts. For now, there's a whole bunch of formulas on page 227 of your textbook that tell you the moment of inertia for various shaped objects: spheres, disks, sticks, rectangles, hoops, you name it. And since most real-world figure objects can be approximated as various combinations of those shapes, we usually don't actually have to do integrals here. You can usually look it up in the textbook, what formula to use. And then we'll combine that with something called the parallel axis theorem, which is a tremendously useful thing. Let's say that we have some blob-shaped object, and let's say that we know where its center of mass is, but we also know that it's rotating about an axis that is not the center of mass. So we have this amorphous shape that is rotating about some axis that is not the center of mass, and we can say that the distance between the center of mass and the axis is d. Now let's say we know what the moment of inertia is about the center of mass. Inertia, not inertial. So we're told that, or we have some other way of finding that, and we know what the moment of inertia is when it's rotating about the center of mass here. And we want to find the moment of inertia about this new axis. To do that, it's actually very easy. I'm not going to prove the parallel axis theorem, but this moment of inertia I is equal to the moment of inertia about the center of mass plus the total mass of the object times d squared, where d is the distance between the new axis and the center of mass. That is a very, very useful thing that you should probably memorize, because you're going to be using it basically on any rotation problem that comes up on the AP test. And now we'll do an example, and let's say we've got a helicopter rotor. It has 3 blades. We're given the length of the blades and the mass of each one. So there it is. We know L, and we know the mass of each blade. And we want to find the moment of inertia of the rotor. And so what we'll need to do is find the moment of inertia of each blade. And we'll treat the blades as sticks, rotating about one end. Now, if we look on page 227 in the textbook, we find a whole bunch of different equations, none of which is a stick rotating about its end. However, we do find the moment of inertia for a stick of length L and mass m rotating about its middle. And that's ICOM because for a uniform stick like these helicopter blades, the center of mass is right in the middle. And so that's 1/12 ml squared. But we want to find the moment of inertia about the end. So we'll use the parallel axis theorem, where d is half of L. So we're going to move the axis L over 2, and so the moment of inertia of one blade is the center of mass moment, ml squared, 1/12 ml squared, plus the mass times the distance it moves, which is L over 2, squared. A little bit of algebra gives us the result 1/3 ml squared is the moment of inertia for one blade. So the moment of inertia for one blade is 1/3 ml squared. Therefore, the moment of inertia for the whole rotor is the moment of inertia of each blade plus the sums of the moments. And so it's just ml squared, where m is the mass of one blade, and L is the length of one of the rotor blades. So it's 240 kilograms times 5.2 meters squared. When you put that in your calculator, you get about 6,500, and the units are kilogram meters squared. And that is how you use the parallel axis theorem and page 227 to calculate moments of inertia. For tomorrow, you should do question 7, If you're interested, I'll show you how to use integration to derive those formulas on page 227, but you really don't need to know that for the AP test.